In this example problem, we're asked to draw all the chair conformations of cis-1-methyl 4-isopropyl cyclohexane. So, there's actually more to this problem than meets the eye, because first things first, we need to convert this name into a Lewis structure. And while doing this, I wouldn't necessarily worry, especially while you're starting out, about the intricate details of the chair structure. Start with a basic cyclohexane ring and add substituents at the appropriate positions, first of all, and with the appropriate stereochemistry and the appropriate orientation before you set out drawing chairs. It just makes things a little bit more systematic and easier that way. Alright, so we have 1-methyl 4-isopropyl cyclohexane. So we can draw the methyl group kind of wherever our hearts please and in whichever position our hearts please. So I'm going to start with a methyl group on a wedge, say right here. And this, of course, since we've laid it down right here, this is now defined as our 1 position. The 4 position is 4 carbons away, 2, 3, and 4. And at the 4 position, we have an isopropyl group. Just to jog your memory, remember that an isopropyl group has a carbon with 2 methyls attached to it and an implicit hydrogen as well, which is often not drawn, but I'll go ahead and draw that in. This is the isopropyl group right here. So we can add that then at the 4 position, and this is cis-1-methyl 4-isopropyl cyclohexane. And so the isopropyl group needs to be positioned on the same side of the ring as the methyl group. In other words, we need to put that isopropyl group on a wedge. So that's the structure we're interested in this problem. And so now we need to convert this into its 2 possible chair forms. How do I know there are 2 possible chair forms? Well, there's one with the rightward slanting chair, essentially, and then we can flip the rightward slanting chair to generate a leftward slanting chair. So let's see what that looks like by, again, just starting out with chair-like skeletons and then filling in the substituents later. So there's an equilibrium here between this chair form and the leftward slanting chair form. And I'm not using the parallel lines method, but I should be to be drawing these chairs. There's an equilibrium between these 2 forms, and it's important to understand what carbons correspond to each other in the left and right-hand structures. So for example, if I call this carbon 1 in the left-hand structure, just because I need to start somewhere, when I flip the chair, carbon 1 actually flips to a downward pointing position, right here. Carbon 2 flips upward, and carbon 2 in the original structure is right here. Carbon 3 started upward and flips downward, and carbon 4 started downward and now flips upward. In terms of axial and equatorial positions, let's draw the axial positions in red here on the original structure, and we'll see what happens to the axial positions upon the chair flip. Well, since carbon 1 flipped from pointing up to pointing down, now the position that was axial in the left-hand structure is now equatorial. And you can see this if you check out an animation of the chair flip that shows you how the groups attached to the cyclohexane ring shift as the ring flips and kind of folds over. And the same idea applies to all the others. What was axial is now equatorial, so these axial bonds here and here, and notice that they're still pointing downward. There are axial positions in the right-hand structure that we're going to fill in later. They're still pointing downward, and those axial positions will be pointing upward in both structures. And so, in terms of wedges and dashes, nothing really has changed. We've just altered the axial or equatorial status of each of these bonds. Now let's fill in the equatorial positions in the left-hand structure in green. And watch what happens to the equatorial positions upon the flip. On carbon 1, what was equatorial is now axial, still pointing downward. Notice it's pointing downward in both structures, but it's now axial in the right-hand structure. And the same idea applies to all the other equatorial positions. The position on carbon 2, which is pointing upward in this structure, is still pointing upward in the right-hand structure. It's just now axial rather than equatorial. So this is just to demonstrate in general how positions change when we go through a chair flip process. For this specific example, we don't need all these intricate details, But this is the general idea. And you can imagine that if we had a cyclohexane that had different substituents at all 12 possible positions, we might have to deal with a situation of this complexity in a hypothetical case. But generally things are simpler than that, and we can deal only with the substituents relevant to our compound of interest. So I'm going to back up and lose all those axial and equatorial positions so that we can focus on the compound we have right here, which is cis-1-methyl-4-isopropyl cyclohexane. So let's add a methyl group in an axial position right here. If we imagine looking down on the cyclohexane ring from this angle, that methyl group is going to be pointing towards us, right? So we would draw it on a wedge. And just to clarify that, the hydrogen on that carbon would be pointing here, and clearly we would want to put that on a dash since it's pointed away from us, right? Pointed back into the plane of the screen or the page or whatever we're looking at as we look down on this structure. If that CH3 is wedged and in an axial position, then the isopropyl group must also be pointing out towards us. And if we draw the two positions on the 4 carbon, we see that the position pointing towards us, right, is this one right here, the equatorial position. And so the isopropyl group here will be sitting on the equatorial position at carbon 4, and a hydrogen will occupy the other spot. Now, what happens when we flip the cyclohexane ring? Well, now the isopropyl group swings up into an axial position. It's still pointing upward. It's pointing upward or wedged, you can imagine, in both cases. And now the once axial methyl group on the 1 position is, again, still pointing upward, but now in an equatorial position rather than an axial position. So these are the 2 chair forms for the compound of interest. And now we're left to judge which is the most stable conformation, which is kind of the second half of this question. Remember that the instability of a particular chair form comes from interactions between axial hydrogens or other axial groups and large axial substituents. There tends to be a lot of steric hindrance going on between axial groups like this. And the smaller the group, the less is that hindrance. So what we're really doing here, since we have a situation where in one structure, let's call it structure A, we have an axial methyl group. And in the other structure, call it structure B, we have an axial isopropyl group. What we're really doing is comparing the size of the axial methyl versus the axial isopropyl. And it's pretty clear to see, just from the outlines we've drawn, that the isopropyl group is larger than the methyl group. That means that there's greater axial steric hindrance in structure B than there is in A, and so B is less stable due to its greater steric hindrance, more energetically unfavorable steric interactions, if you like, and A is more stable. Because although it does have some 1,3 diaxial interactions going on between the CH3 and the axial hydrogens here and here, they're clearly not as severe as those going on with the larger isopropyl group. So the more stable conformation in this case is structure A, our rightward slanting chair with the methyl axial and the isopropyl group equatorial. In problems like this, you can essentially ignore the contribution of the equatorial substituent to the overall energy of the conformer. It's really about which substituents are axial and their relative sizes in the 2 chair conformers.